did play a large role in this one as well. I have a couple of mesonet temperature that show all the little mesonet temperature stations, and you'll see the differences, and you can pick out where the terrain was higher and lower just by looking at the temperatures. The dew point and surface relative humidity analysis will show why areas at the same elevation and latitude saw different results. It's interesting, parts of northeast Massachusetts and southeast New Hampshire at 100 feet above sea level got destroyed with ice, where just west of the Worcester Hills in the Connecticut River Valley at 100 feet got nothing. They got 33 in rain. And we're going to see why, even though they were at the same elevation and the same latitude. And the longitude certainly played a role too. And we're going to look at the forecasting side. Models, some of the biases we were talking about. In the thread, we had a long forecasting thread for that storm. And something that we can point out is some of the model biases that occur, especially during icing events. And a lot of the times the models do not forecast. They always tend to under-forecast the amount of cold air damming that occurs to the west of the surface low track. It'll always try to get you up to 38 or 40 in rain, and it stays 31 in freezing rain for the whole storm. And we're going to see how we can use that to maybe forecast these events more accurately as we go forward. Okay, look at the models leading up to the storm. This is Mike Exter posting.
I've never seen that before.
This was his first reaction to the NAM. Oh, there we go. That's kind of a little clearer. And so this was his first in-depth analysis of the NAM. All right, now here's my in-depth analysis. And then down here was a pretty good exchange that I picked out. This was a good exchange. We were talking about, you can't see my response they quoted. What I said here is that GFS didn't trend much from the 18Z with its surface track. Would still likely be a big problem for most of the interior, even if though verbatim, it doesn't have the freezing line southeast of a Jaffrey to Pittsfield line. The crappier resolution, excuse my language, the crappier resolution probably can't resolve the low-level cold very well. Now, we were looking at the GFS, which has as many of you are aware, the GFS has a much lower resolution than a mesoscale model like the NAM. So the GFS was trying to forecast a 40-degree rainstorm for much of the interior, despite a surface low track over, the Cape Cod Canal or something like that. It was well in southeast New England. And so Ryan, RFHPSU, he's a common poster around Southern New England, he says, agreed, well, surface low track over Gone, which is New London, Connecticut, southeast Connecticut, and then I think had the track going over like Providence or southeast Mass. Would still mean ice for many inland elevated areas. And then Exter's response is talking about how, again, he was agreeing that the resolution is probably causing a lot of problems, because what you want to look at is the surface track, and then based on what we know about the GFS and its bias is not to handle the low-level cold very well, and not to handle the little mesoscale aspects of these coastal storms because of its resolution. Naturally, I mean, you just can't see it. Its pixels are too big, and the resolution is just not as good. But of course, as we said, look at our reactions to the NAM. The NAM was obviously showing something different, and that's because it could handle the low-level cold, and it could handle the inversion much better than the GFS was able to do. Okay, so here's the NAM buff kit sounding. For those of you in the back, you can't see, this dashed line right here comes right along. That is the 0 Celsius line, the freezing line. So what you can see is that the 850s are basically, I mean, this is like plus 10 850s. So if you just looked at an 850 temperature map, you'd have no idea what was going on. You have plus 10 850s here, but yet you fall this back down. By the time you get to about 975 or 925 millibars, you have temperatures about -5 Celsius, and that, or -4, -5 Celsius, which is well down into the 20s. And the surface, as you can see, is below freezing, probably about 29 or 30 there. But look, there's a nice little bit of a pocket of dry air right near the surface, and that's important in this event. You can see that the green there is the dew point, and you can see how it's separated from the temperature at the base. And that means that there's some dry air right near the surface, and that's going to be that ended up being a very key component to this ice storm. As bad as the NAM showed, it was actually interesting. The NAM was actually a little bit too cold at the surface for this event. It showed temperatures in the upper 20s for pretty much the whole event, when in reality, the temperature really never dropped below 30 in a lot of spots, but yet the icing was still really bad. We're going to see why in just a second. Oh, here's the, after all the model analysis, here was the Taunton warning advisory map from 5 p.m. the day before the event started. And this was actually, I wanted to put this up because it's actually verified extremely well. This dark purple area you see, that's in extreme northwest Connecticut and then central and western Massachusetts, was the ice storm warning. And just advisories for north-central Connecticut and then interior northeast Massachusetts. The only place where probably the warning probably could have, in retrospect, of course, this was one of the weird parts about the event, northern Essex County got hit pretty hard in this event. But overall, this was actually a very, very good map for a very tough event to forecast for. This was actually a winter storm warning up here, because there was supposed to be a little more sleet involved in southern New Hampshire, not just 100% ice. But this actually ended up verifying very well, which is a good kudos to the Taunton. I know Mike was part of he was part of that forecasting. I think you were the first one to put the watches up in that. So it was very, very good forecast by the Taunton office. Now, I wanted to post this. This looks like an 850 map. It's actually 950 millibars. And I wanted to post this because this is really important. Well, we saw the 950 millibar low, and it tracked up right across southeast New England. And what you're looking at here is there's just a ton of warm air advection going on out ahead of this. But it's very elongated, and this high pressure up here, you can see there's almost a weak circulation right in here over northern New England. And an even stronger one up here over northeast of Maine. You can see this anticyclonic flow. And it just gets caught up in that low, in the cyclonic circulation, and you can see these arrows are just feeding straight down through southeast Maine into New Hampshire and into interior southern New England, even all the way down to northwest New Jersey, which got a lot of ice above about, I think it was about 800 or 1,000 feet. They had a lot of ice in extreme northwest New Jersey as well. And what you're seeing here, this is 950 millibars, right about the coldest point in the sounding, maybe just below it. You're seeing just a tremendous drainage of cold, and this air was a little bit dry too, as we'll see on the next, especially below 950 millibars. There's some dry air in there, and just a tremendous drainage of low air from the of lower temperatures at 950 millibars, colder, drier temperatures coming from this high pressure up here. And that is just a red flag that immediately should go up when you're forecasting, when you see that type of drainage coming from a very cold air source up here in Nova Scotia. And that was a key component to this event, as we're going to see here on these temperature and relative humidity maps just exactly how this played out. And remember this map when you see those, because this was the cold air source draining right down into the interior.